Hello. Now we are going to look at an introduction to fractions. We're going to look at the different ways that we can write fractions, where they come from, and how to do equivalent fractions or how to compare fractions. To begin with, a fraction is where we break up some unit, some whole object, into equal pieces. So if we take our large rectangle here as being one unit, what fraction have we colored in green? We would say that we would have one out of the two equal pieces marked as green. So we would say that we would have half of our unit would be green, because we have one out of the two pieces, our two equal pieces of our unit would be green. Now, are there any other ways that we could break up our unit and have it be the same fraction overall? Well, what we could do is break this up horizontally. We could break up it in half this way as well. So I'm going to mark that in. When I have done that, when I have broken it in half this way, I can now see that I have broken up my unit, my large box, into 4 equal pieces. So I am going to have, I've broken it up into 4 pieces, and how many of them are colored in? Well, 2 of those 4 pieces have been colored in. Could I break it up again? Well, I could break it up. I could have each of these pieces here and break it up into 8 equal pieces. So I'm going to mark that in now. When we have broken this up into more halves, having what we had for our blocks, we find that we now have 1, 2, 3, 4, 5, 6, 7, 8 pieces. And how many of those pieces are colored in? We have 1, 2, 3, 4 of them colored in. So we had half of our block colored in, and now we've broken it up into 8 equal pieces, and 4 of them are colored in. How could we say this mathematically? How could we argue that this makes sense mathematically? We can see visually why it's happening. If we break up, say, for our halves to 2 quarters, why does that end up being the same fraction of our shape overall? Because if we break it up, if we break our pieces up into twice as many chunks, we're going to have twice as many of those chunks. If we break our unit up into 4 times as many chunks, we're going to have 4 times as many of those chunks. What we can see is, going from here to here, we have effectively doubled the top and the bottom of the fraction. But we can't mathematically, from a structural point of view, we can't just say, well, we multiply by 2 here and we multiply by 2 here. These 2's just sitting out in the middle of space don't make sense within the language of maths. So structurally, when we are going to talk about these fractions being the same as each other, they describe the same fraction of a unit overall. They are equivalent because they are equal strength, they're equal in value. When we want to talk about equivalent fractions and how to create them, what we are going to do is multiply fractions together. Now, mechanically, we haven't done that yet, or we may not have seen that before. But this doubling the top and doubling the bottom that we are doing here to make these 2 equivalent to each other is actually fraction multiplication. And we will look at that in more detail shortly. But what we are doing from a logical point of view is, if we break up our unit into twice as many pieces, we end up with twice as many of those pieces. If we break it up into 4 times as many pieces, then we have 4 times as many of those pieces. That's the logic underlying this business of a half being the same as 2 quarters, a half being the same as 4/8. So that's what we are initially looking at. What is a fraction? It's the number of pieces out of our unit that we have colored in. And we can see that there's more than one way to describe that fraction. We would be able to say that it's half of the unit, or we could say it's 2 quarters of the unit, or we could say it's 4/8 of the unit. And there would be an infinite number of ways of describing how we would break up this unit into equal sized pieces, and then we count up how many of those equal sized pieces we've got, and that gives us the fraction of the unit we're talking about. Now we can also have multiple units. You can see that this bar here and this bar here are the same size. That's very important. If they're not the same size, then we wouldn't be comparing like with like. So this is one unit, this is another unit. And it's important that they are exactly the same shape and size. Otherwise, we can't add them up meaningfully. We have to compare like with like. So what have we broken up these two units into? Because we've broken up our units in the same way. We've broken them up into 1, 2, 3, 4, 5 pieces. We've broken up both of them into 5 pieces. So how would we describe the total amount that we have got? Well, we could say that we had one whole unit. So we'd have one whole unit, and we would have a little bit extra. How would we describe this little bit extra compared to the size of our overall unit? Well, we would have 2 out of 5 of our pieces are colored in. So we would say we'd have 2/5 of our second unit are colored in. So in total, we'd have 1 unit and 2/5 of a unit, and that's the total amount that we've got colored in of these unit blocks that we have got, our bars that we have here. Now sometimes it's useful to describe the quantity we've got, the amount that we've got in this way, but really we only use it for a final answer. This is called a mixed number because we have units and fractions sitting next to each other. And mathematically what it means is we have 1 plus 2/5. We often don't bother writing down the plus, but that's essentially what this means, and that can be important to keep in the back of our minds. It means 1 unit plus 2/5 of the same sized unit. But more regularly, we are going to want to write this as an improper fraction. So here, these are proper fractions. The number on the top is smaller than the number on the bottom. Here we actually have more fifths than we would for 1 unit. We have 5/5 here, 1, 2, 3, 4, 5, and then we have another 2, 6, 7/5 of the same sized unit. So we would end up with 7/5 would be how we would describe that as an improper fraction. And that is more regularly the way we are going to write our fractions in maths. So let's have a look at some more equivalent type fractions. Is there any other way that we could write the fraction 10/3? So are there any equivalent fractions to that? Well, if we start with 10/3, we know that if we broke up, so our units here have been broken up into 3 pieces, and we can see that we have more than just 1 unit's been broken up because we have 10 on the top. So we have 10/3, which is definitely more than 1 unit because 3/3 would be 1 unit. So if we broke up our units into twice as many pieces, then we would end up with twice as many of those pieces. So this is the chunks, this is the pieces we've broken up our units into. If we break this up twice as fine into twice as many pieces, equal pieces, then we would end up with twice as many of those pieces. Again, this is actually fraction multiply. We will deal with that later on. But logically speaking, if we broke this up into each unit into 6 pieces instead of 3 pieces, we would end up with twice as many of those pieces. So 20/6 must be the same as 10/3 because it describes the same fraction of a unit, or in this case of multiple units. We can do this for any number of units. We could start with 10/3 and we could break this up into 3 times as many pieces. So if we broke that up into 3 times as many pieces, we would end up with 30 pieces in total, and we'd have broken everything up into each unit into 9 pieces. How would we write 10/3 as a mixed number? Would be another question that we could think about. So we would have 10/3. Well, how many complete units do we have in 10/3? Well, we know 3/3 would be 1 unit. So we'd have 3/3 and 6/3 would be 2 units, and 9/3 would be 3 units. But then we don't have enough to make the next one. So we'd have 9 of our thirds taken up, making 3 units, and then we would have 1/3 left over. And that is how we can construct our mixed numbers from our improper fractions. But improper fractions is really what we will spend most of our time on. We have another one here. We have 4/5. What would be a fraction that would be equivalent to 4/5? Well, we could just say, if we break that up into twice as many pieces, we would end up with twice as many of those pieces. So we would just end up with, if we had 10 pieces we'd broken our unit up into, we would end up with 8 of those little pieces. Now we can do this in reverse effectively. If we look at all of our equivalent fraction work that we've done, these look a little bit like factor pairs. If we think about the factor pairs of 20, 10 and 2 would be a factor pair of 20. If we think of 6, 3 by 2 would be a factor pair of 20. So when we want to simplify fractions, we can think about the factors involved. So can we think of a common factor to 6 and 8, just like 2 ends up being a common factor of 8 and 10 here, because that's what we multiplied above and below by. What would be a common factor above and below here? Well, it would be 2 again. I could write 6 as 3 by 2, and I could write 8 as 4 by 2. And that would end up logically being the same as 3 all over 4. We'll look at in more detail as to why this is later when we do fraction multiplication, but what it comes down to is that 2 divided by 2 is just going to be 1. So we'd end up with one group of 3/4. How could we simplify this? Well, is there a common factor top and bottom that we could simplify with for 25 and 20? Well, the highest common factor of them would be 5. So I could write that as 5 times 5. 25 is 5 times 5. And 20 is 5 times 4. So I'd be able to say that is going to be the same. This is essentially just 1. 5 all over 5 is just going to be 1. So I'd end up with one group of 5/4. Now, if we want to compare fractions, we need to be comparing like with like. Just like we talked about, the units must be the same size if we want to add them up. If we want to compare fractions, we have to compare like with like. If I want to answer this question, is 2/3 greater than 3/5? I need to be talking in the same sized chunks, in the same sized pieces. I can't directly compare thirds and fifths. So how would I get them to be the same number? Well, we effectively do the same thing as we did for equivalent fractions, but we're trying to end up with the same number underneath both fractions so that we're comparing the same sized pieces. So what would be the number that we could get underneath both of these fractions? Well, 15 is a common multiple of 3 and 5. So if I got both of these over 15, if I broke this up into 5 times as many pieces, and I broke this up into 3 times as many pieces, I would end up with 10 all over 15 is bigger than 9 all over 15. 5 by 2 is 10, 3 by 3 is 9. Is that true? Yes, it is. So I need to get the same denominator to compare my fractions. Here, I would want to see what would I break up my fractions into so that I would end up with the same denominator, so I could count up the same number of pieces. Well, 12 would be the lowest common denominator, would be the lowest common multiple of 4 and 6. So I'd break this fraction up into 3 times as many pieces and this fraction up into 2 times as many pieces. And I would end up with 9 all over 12 is greater than 10 all over 12. And again, that's not true in this case. That would be smaller. So we can see once we are counting in the same sized pieces, we can just see which number we have more pieces of. And that is how we can compare our fractions. So that is what we need for now.